a deceptively simple question, just a time dilation question, but it's very easy to get ourselves confused as to what the TV and the T0 is. And I want to show you two ways. One, if you like, is the right way, and the other way is the way to make sure it happens correctly when you're in the pressure of an exam and it's easy to get confused. So before we do anything, even in an exam, we're going to stop, we're going to take a moment, and we're going to draw ourselves a summary step. Okay, so the question puts us in this frame of reference here, the frame of reference on the Earth. We're an earthbound observer looking in at a spacecraft at a clock through the window as that spacecraft goes past us at 0.96 c. And we're going to always measure our velocities wherever we possibly can in terms of c, fractions of the speed of light, and whatever other units are convenient. In this case, because it's a straight time dilation, we're just seeing how much time is dilated, we can use whatever units we want. And we're going to stick with minutes because that works quite conveniently for this question. So really the question arises, what is the TV and what is the T0? Well, our temptation is to think the TV is the moving thing, and of course that's the spacecraft, isn't it? But no, it's not, because if you're in the spacecraft, it's the planet that's moving. So TV and T0 don't refer to what's moving and what's stationary. They refer to whether the event is in, what frame of reference the event is in, okay? So while the question writer might want to put us on the planet, it's actually best if we stop and think, what frame of reference will it be easiest to put ourselves in? And the best and the easiest one is to put ourselves in the frame of reference where the event is happening. Okay, the event that we're looking at is the hands of this clock ticking through 90 minutes. So let's put ourselves in that frame of reference. Then our T0 is going to become 90 minutes, and we're going to calculate our TV. We're going to ask what would be the time on the moving frame of reference, which in this case is the planet. See, it doesn't seem very logical because planets don't move, but of course they do. It's all relative movement. We don't know who's actually moving. So what we're going to do is we're going to put ourselves in the frame of reference where the event is happening, and that's sometimes a bit hard to work out what the event is. So here's the first approach, is to try and work out which frame of reference is the thing happening in that we're trying to time, and put ourselves in that frame of reference. What we do know is what the time is, the elapsed time in that frame of reference. So that's the easiest frame of reference to put ourselves in, and then we're trying to calculate what the time would elapse on the planet's frame of reference according to this guy here. And that actually makes the question quite simple. It's a fairly trivial application of the law. Now, because we're going to do things in terms of the units of the speed of light, then one lot of the speed of light is just 1, which simplifies this down a whole lot because it just becomes c squared becomes just 1 squared, which becomes 1. So we're just trying to then calculate this. So it's simply going to be T0 on 1 minus v squared, which is going to be equal to 90 on the square root of 1 minus. Okay, don't forget to put the squared signs in here. So let's have a go at doing this. Bang, and there it comes out, 321 minutes. 300 minutes is 5 hours, so it's 5 hours and 21 minutes later. So it started at 9 o'clock, 10, 11, 12, 1, 2. It's going to be 2 o'clock, 21 minutes past 2 o'clock in the afternoon. So it's going to take a lot longer. Now, when you think about it, that makes sense because this person here is looking at that clock and seeing that clock run slow. So while he sees that clock's going very slowly, ticking through 90 minutes, he knows that in reality, in his frame of reference, time is running at its normal pace, and so a lot more minutes are going to have gone by. And that's really the second approach. If you're not quite sure which way around the TV and the T0 are going to go, work out what's logical. Okay, so there's only 2 possible answers you could get. You could have the TV and the T0 swapped around. Just swap them around. The other one gives you a lot shorter time period than 90 minutes, and if you think about it, that doesn't make any logical sense. It's got to be a number greater than 90 minutes, and the only one that gives you the number greater than 90 minutes is this one here. So 2 approaches. Think carefully about what frame of reference you're going to put yourself in. Whatever frame of reference the question writer uses, think about what frame of reference is most convenient to put yourself in, and then that'll determine what the T0 and the TV is. And generally, put yourself in the frame of reference where the event is happening. In this case, because we're told 90 minutes inside the spacecraft, that's the logical place to put ourselves. The second approach is to go, I don't know what the TV and T0 is, let's just try it both ways around and see which number is the logical one. And so that's when you've got to use your logic. You've got to remember that you're going to watch a moving clock and see it running slow. So if a clock is moving relative to you, you will see it run slow. This person doesn't see the clock run slow in the spacecraft. This person does because the clock is moving relative to them. This person here would see the clock on the planet run slow. Okay, so it's about choosing either the frame of reference you go in, or just going, well, I'll just do it from both ways around and pick the number that gives me the right answer.